chapter 1, section 4, which is over limits. So we'll be talking about limits and what they are. So first off, what is a limit? We'll also find limits using tables and graphs. We'll talk about properties of limits and use those properties to find limits algebraically. And in your homework, you'll see something called the average cost function. So let's start with what is a limit. So if we have a graph, we're looking at the graph of a function. We say the limit of the function, the limit of f of x, as x approaches c, so x is getting close to c. We're talking about x values getting close to c. So from the left and right, we want to get close to c. We say that is L, right? So that L gives us a height, right? The function gives us the height of the graph. So as x approaches c, as x gets close to c, we say that limit is L. And here's our notation for that. So this reads the limit as x approaches c of f of x is L. If you can get as close as you like to L, right? So we can get closer and closer to this height by taking x values close enough to c, right? What does that really mean? That means that from the left and from the right, if you trace this graph, from the left as you go towards that x equals c, you trace it and you're reaching that height L. And from the right as you go towards x equals c, it's also going to the height L, whatever that might be, right? Whatever number that is. This notation is very important, right? So make sure you familiarize yourself with it. C is just some constant, so we'll often have, like the limit as x approaches 2 or something like that. And we'll have to figure out what these limits are. So that is what a limit is. It's what your function is getting close to in height as x gets close. So when we write this limit as x approaches c, what we mean from there is that x is getting close to c from the left and the right. But we can be more specific and put a little negative sign to indicate we're only approaching from the left when x is less than c, or put a little plus sign to indicate we're only approaching from the right when x is greater than c. And we call that the limit from the left and the limit from the right. Sometimes I'll also say the left hand and right hand limits. And in the graph, that's just what height your function is approaching as you only come to c from the left side or only from the right side. So we then have a theorem, a fact, that the limit exists and is equal to L if and only if, right? So only if the left-hand limit exists and is equal to the right-hand limit, and that they are both equal to L. So the limit exists only if the left-hand limit exists and the right-hand limit exists, and they are the same. What if a limit doesn't exist? How do we figure that out, or what is the notation for that? Well, if I'm talking about limits not existing, of course you should think of Mean Girls. So let's take a second look at this.
I never remember anything about limits. Limits. That was the week Aaron got his haircut. Oh God, he looks so cute. Okay, focus, Katie. What was on the board behind Aaron's head? If the limit never approaches anything, the limit does not exist. The limit does not exist!
Alright, so she said if the limit never approaches anything, then the limit does not exist. Well, what that means is that if the left side isn't the same as the right side, the limit does not exist, right? So that means the function isn't approaching the same thing from both sides. And when that happens, we say the limit does not exist. Okay, so here let's look at some examples. We'll be given a graph, and I'm going to ask to find some limits. So we're taking the limit as x goes to -2. So we're talking about x at -2 is over here. It says find the limit as x approaches -2 of f of x. So what we do, since we know the limit exists if and only if the left-hand limit is the same as the right-hand limit, we need to figure out what the two of those things are and see if they're the same. So to figure out the limit from the left, we start somewhere to the left of -2, so over here at -3, -4, and we want to move to the right, following this graph, and see where we end up when we hit -2. Right? So we move to the right, and we see that when we hit this x value of -2, we're at the height -3. So from the left, the limit from the left of this function as x approaches -2 is -3. All right, so what we want to see if is that the same as the limit as x approaches -2 from the right. So we'll start over here to the right of -2 and trace the graph moving to the left towards -2. And we can see that as we get close to -2, the height we're at is -3. So since the limit from the right was -3 and the limit from the left is -3, the limit exists and is -3. So that limit is -3. Right, what about f of -2? Well, that's this solid dot right here. Right, so what is that? That means that at -2 we were at height -5, so that is -5. And notice those don't have to be the same thing. Where a function gets close to as you go to -2 does not have to be the same as what the function is defined to be. All right, what about as x approaches 2? So now we're looking at the limit as x goes to 2, positive 2, of this function. So again, we need to check the limit from the left and the limit from the right and see if those are the same. So for the limit from the left, we start somewhere to the left of 2 and we trace the graph, see what height it's going towards as x moves to the right towards 2. So we start on the left and we want to move towards 2, tracing this graph. And we can see that we get close to this height 4. So the limit from the left is 4. To determine the limit from the right, we start somewhere to the right of 2 and we trace this graph to the left towards 2. And we can see that ends up somewhere up here at looks like 6. So the left-hand limit, the limit from the left was 4. The limit from the right was 6. So since those are not the same, this limit does not exist. Right? So you can see when a limit exists, it's somewhere where maybe just a spot was removed, or dot. Whereas if these two places are going somewhere different, this function, sorry, is going to somewhere different from the left and the right, then that limit does not exist. All right, what about f of 2? For f of 2, we go to that solid dot, which was here. And so that means that at x equals 2, this function is at height 4. So just because the limit does not exist doesn't mean the function's not defined, right? That closed dot here at 4 said that the function is defined to be 4 at 2, even though the limit did not exist. What about limits to infinity, right? So we'll be looking at these on the graph. The limit as x approaches infinity. So as x approaches infinity, what that means is that we're taking greater and greater and greater values of x. So we want to look at what x is doing as it goes off to the right forever. So we trace this graph and see what's it doing as we move off to the right forever. And it looks like it's just going to keep going all the way down to -infinity. So you could write -infinity. But that's also not a number. Whoops, I forgot my D. So we say does not exist. D-N-E. What about to -infinity? The limit as x approaches -infinity. Well, same story. That time we would be moving off to the left forever, and it looks like it would just keep going like this, and eventually go as far. Okay, let's look at some properties of limits. So one, if k is any constant, any number, then the limit as x approaches c is just k, right? So that would be like the horizontal graph of y equals k. No matter where you're looking, that height is always k, right? One other way to think about that is there's no x's in here. So it doesn't matter what x is, this still just spits out k. So the limit of a constant is just that constant. If p is a polynomial, right, this is our next property, then the limit as x approaches c of the polynomial is just p of that polynomial. So what this means is that you can just plug in x equals c to that polynomial, and that's going to be your limit. All right, so we have a lot here. So what this says is if r is a rational function, so that just means it's one polynomial divided by another. So if your limit is something like the limit of one polynomial divided by another, then again, you can just plug in x equals c and see what you get. And whatever that is going to be your limit as long as that denominator is not 0. If that denominator is 0, we'll run into some issues and we'll address those. Okay, more properties of limits. So now we're going to assume that the limit as x approaches c of f of x exists, and the limit as x approaches c of g of x exists. So if those two limits exist, then if we add or subtract our functions and then take the limit, that's the same thing as taking the limits and then adding them or subtracting them. If we multiply our function by a number, we can pull that number out and just take that number times the limit. And if we're multiplying our functions, then we can just multiply the two limits independently. Right. Along that same line, if we're dividing our functions, then we can just take our limits on the top and the bottom and divide those, as long as, again, that denominator is not equal to 0. If it is, then we'll have to do something else. And there's two more properties that are really the same in disguise. And what that means is that if you have a function raised to the nth power, then you can just take the limit and then raise that limit to the nth power. Or if you have a function and you're taking the nth root of it, then you can just take your limit and then take the nth root. So all of this amounts to just try to plug in x equals c first. And as long as you don't get a denominator equal to 0, you'll get a number, and that is what your limit is. Okay, so let's look at an example, right? So we have, this is a rational function. It's one polynomial divided by another. But we know that when we're finding these limits, step one is just try to plug in this case, x equals 3. So what do we get when we do that? We get 3 plus 1 over 3 minus 1 squared. So right, we're exploiting all of those properties we just went through that tells us as long as we don't get a 0 on the bottom, we're allowed to just plug this in. So what is that? It's 4 over 2 squared is 4. And so 4 over 4 is 1. So that is what this limit is. Right, so we exploited all the properties we just went through and just plugged in x equals 3. Since we didn't get a 0 in the denominator, we just boxed our answer, and that number is the limit. So look at, it's the same function, but now I'm looking as x approaches 1, right? So first step again, just try to plug in 1 and see what you get. So x equals 1, so we get 1 plus 1 over 1 minus 1 squared. But that is 2 over 0, so that over 0 should raise a big red flag to say this doesn't work. And in fact, if we graph this function, which I've done over here, you can see that here at x equals 1, from the left, this function is shooting off to infinity, and from the right, it's shooting off to infinity. And so that limit does not approach any number. So this last example where we plugged in x equals c and got some number that's not 0, in our case we got 2, divided by 0, that's called an undefined form, right? So if you have a non-zero number, like we had a 2 divided by 0, then that limit is called an undefined form, and in that case, the limit does not exist. So if you plug in x equals c and you get something that's not 0 in the top and you do get 0 on the bottom, then you can just say, okay, the limit does not exist. All right, so how about this guy? All right, we've got another limit. And what we want to do is, just like before, try to plug in x equals 2. So when we do that, we get 2 squared is 4 plus 2 minus 6 over 2 minus 2. And 4 plus 2 minus 6, that's 0 over 2 minus 2 is 0. So you might think, oh, hey, I got a 0 on the bottom, so this limit does not exist. But since we also got a 0 on the top, that is not necessarily true that it doesn't exist, right? This isn't k over 0 where k is non-zero, like our undefined form. In this case, the limit might or might not exist, and we have to keep going to check our work. So what I'm going to do here is graph this guy. And so you can see that if I graph this guy, as x approaches 2 from the left, I'm actually approaching a height of 5. And from the right, I'm also approaching 5. So if I had this graph, I knew the limit exists and it's 5, but I just have a hole there, right? And that hole is given by that denominator being equal to 0. That's where that shows up algebraically. When we're finding these limits, we cannot just graph them. We have to figure out, how do we find this limit algebraically? So this is how we do that. Anytime we substitute in x equals c and you get 0 over 0, that's called an indeterminate form. And what that means is that you're not yet able to determine whether or not the limit exists. So how do you do that? How do you actually find the limit? Well, what you do is you factor the numerator and factor the denominator, and there will be a common factor that you'll be able to cancel and get rid of. Every time you have an indeterminate form 0 over 0, the numerator and denominator will have a factor in common that's causing that problem, so you can factor the numerator and factor the denominator and cancel out the problem term. So in this example that we just had, we started by trying to plug in, and we got 0 over 0. So we know that that's not going to work, and we need to continue. So we haven't taken the limit yet. So you have to keep writing this symbol that says the limit as x approaches 2. And now we need to factor the numerator. So x squared plus x minus 6. Well, that factors to x plus 3 times x minus 2. And then the bottom's already factored, x minus 2. And we can see that we have an x minus 2 in the top and an x minus 2 in the bottom, so those cancel. And you get the limit as x approaches 2. And now we just have x plus 3. And now when we substitute in, we get 2 plus 3, which is, whoops, got a little ahead of myself there. 2 plus 3 is 5. And that's our answer. And that's, you can recall that that's what we got on that graph when I graphed this a second ago. All right, notice that this problem term that canceled out was x minus the thing we were going towards. Right? So if we're taking the limit as x approaches 2 and we get a 0 over 0, then we know that x minus that 2 is what's causing the problem. And so that should be a factor of the numerator and denominator. So similarly, if you were instead taking the limit as x approaches 7, and you got this indeterminate form 0 over 0, then you know x minus 7 would be the thing that should cancel out and would be a factor of both the numerator and denominator. If you were taking the limit as x approaches negative 7, then x minus negative 7, which is x plus 7, that would be your problem guy that you know you should be able to factor out and cancel. All right, so anytime you have this indeterminate form 0 divided by 0, when you try to substitute in, you should be able to factor out that x minus c, cancel it, and then substitute in to get the actual limit. And there's our graph where we did see that as x approaches 2. Okay, so I've talked about limits to infinity when we looked at the graph. Now let's look at them algebraically. Right, so this symbol limit as x approaches infinity of f of x, that tells us what the function is doing as x goes to infinity. So that's when we plug in larger and larger and larger and larger x values. On the graph, that's what height your function is approaching as you move to the right forever. Similarly, the negative infinity, that would be what is happening as x gets more and more and more and more negative. And on the graph, that would be what height your function is approaching as x as you move to the left forever. So when you're doing this, you can still try to just substitute in, but of course you can't really just plug in infinity. What you have to do is just look at it and think, well, what's going to happen if I plug in larger and larger and larger numbers? So let's look at an example of that. So if I look at the limit as x approaches infinity of x to the 4th power, right? So what if I plug in larger and larger and larger numbers to x to the 4? And so for example, 10 to the 4, 100 to the 4, 1,000 to the 4. Right? So you can see pretty easily that this limit is going to blow up to positive infinity, because x to the 4, when you plug in larger and larger and larger numbers, it's just going to keep spitting out larger and larger numbers. And so we would say that this limit does not exist. And so here we have a property that as long as you're looking at an n that's greater than 0, the limit as x goes to infinity of x to the n never exists, right? It does not exist no matter what that n is, as long as n is greater than 0. So x to the 4, 4 is greater than 0, so that limit would not exist. If n is less than 0 in this example, then it looks like this. And so if you have 1 over x to the n where n is greater than 0, that's the same thing as the limit as x. Oops. That's the same thing as the limit as x goes to infinity of x to the n, right? But remember, flipping it to 1 over x to the n, that would be saying we're taking negative numbers. So these are the same thing. I'm just rewriting it a different way. So if you have something like 1 over x to the n where n is positive, then that limit is always 0, right? As you plug in larger and larger numbers, this denominator blows up, and 1 over 10, 1 over 100, 1 over 1,000, that's always going. All right, so here we've got a limit as x goes to infinity, but I've got an x squared plus 3 over x minus 2. So how can I figure out what that does? Well, I'm going to start by graphing it. Right, I've graphed this function. Remember, the limit as x goes to infinity is what happens as we move to the right forever. And you can see that this function is going to just keep blowing up to positive infinity forever. And so this limit does not exist. Now we will be taking these limits as x approaches infinity, but we don't want to just use the graphs to figure out what they are. We need to be able to figure out how to determine those limits as x approaches infinity algebraically. Right? So in this example, last time, we had behind the scenes another indeterminate form showing up, where we had an x squared on the top and an x on the bottom. So those both were going to infinity. And this is how we figure that out. If we're taking the limit as x approaches infinity, we're going to use this thing called the dominant term property. Right? So for the limit as x approaches infinity, we use this dominant term property. And what that is that you can ignore everything except the dominant term in the top and the dominant term in the bottom, where the dominant term is the guy with the highest degree. And so let's look at this in practice and learn from example here. So here I've got the limit as x approaches infinity, and I've got some polynomial divided by another polynomial. So using my dominant term property, since I'm taking the limit as x approaches infinity, I know this is the same as the limit as x approaches infinity. And I only need to pick the guy with the highest degree in the top and the guy with the highest degree in the bottom. And I get 4x to the 4 over 9x cubed. And now I can cancel an x cubed, and I'm left with the limit as x goes to infinity of 4/9 times x. And I know I can pull that 4/9 out, and this is x to the 1. So I think what happens is I plug in larger and larger numbers, and that's going to blow up to positive infinity, so this limit does not exist. So our dominant term rule says that we can drop off all this extra crud and only look at the two terms, one in the top, one in the bottom, that have the highest degree in the top divided by highest degree in the bottom, and just see where that goes. However, when using this dominant term property, this step is not necessary, right? If you know this property, then you can just look and see the highest degree in the top is a 4, and the highest degree in the bottom is a 3. So since 4 is greater than 3, this limit's not going to exist. So here's how you would show the work for that. You would just say that the highest degree in the top is 4, and that's greater than 3, which is the highest degree in the bottom. And if you tell me that, that's plenty of justification. I know that you're referencing the dominant term property to say that this limit does not exist. All right, so however you want to say that, just reference that the degree in the top, the highest degree of 4, is greater than the highest degree in the bottom of 3. So since the top is greater than the bottom, the limit does not exist. All right, how about this guy? We have the limit as x goes to infinity. And again, we have a rational function, one polynomial divided by another. So we know we can use the dominant term property. So let's find the highest degree in the top. Well, it's 2. And the highest degree in the bottom, it's not out at the front. It's this guy in the middle, an x to the 5. So you would say since the degree, right, this is another way to say it. It's different than what I did last time, but just as good. The degree of the bottom, which is 5, is greater than the degree of the top, which is 2. Well, what does the dominant term say? It says the limit as x goes to infinity of all that stuff equals 0. Right, so since the degree on the bottom, the highest degree on the bottom was greater than the highest degree on the top, the limit equals 0 by the dominant term property. All right, what about this guy? So here we have the limit as x approaches infinity of 2x cubed. That's the highest degree. So we found our highest degree. On the bottom, what's our highest degree? Well, it's also an x cubed. Right, so we're not quite sure what's going to happen yet. Let's see. If we have the limit as x approaches infinity, we know that we can drop off all the rest of this stuff, so we get 2x cubed over 3x cubed. And now we can cancel these x cubes, and this is the limit as x approaches infinity of 2/3. So using our rule of the limit of a constant, there's not an x in there, and so we just get 2/3. So what the dominant term property says is that if the degree on the top is the same as the highest degree on the bottom, then you just look at the numbers out in front of those guys and take their ratio, and that is your answer for that limit. Summary of that dominant term rule. If you end up with an infinity over infinity, or if you're taking the limit as x goes to infinity, then there's 3 options. If the degree, when I say degree here, I mean the highest degree of the numerator is less than the highest degree of the denominator, right? So if the bottom is bigger, then the limit equals 0. If the highest degree in the numerator is the same as the highest degree in the denominator, if they're the same, then the limit is the ratio of those coefficients in the dominant terms. If the degree of the numerator is greater than the degree of the denominator, so this is the top is bigger, then the limit does not exist. So this is a summary of the dominant term rule. So whenever you're looking at these limits to infinity, just tell me what these degrees are and tell me what the limit is, whether it's 0, a number that's the ratio of these coefficients, or that it does not exist. And that's everything from 1.4. So there's the homework, and there is a yawning Tucker.